Welcome all of you for today's session. So today is the week 12 live session for the Power System Engineering NPTEL course. My name is Gagan Meena and I am third year PhD student from Electrical Engineering Department at IIT Bombay. So to start with today's session, we will be following this flow for today's session. First of all, we will go through a quick overview of week 12. And then we will discuss some questions, problems related to week 12. And then finally, you can ask your doubts. In between also, if you have any doubt, you can ask. So, just to remind you, the deadline for submission of assignment 12 is April 17th. So please submit the assignment before that. And the links for the live recording the live sessions recording links you can find on the portal, where a Google Sheet, a link to Google Drive is available, where you can find all the links for the recordings. You can also directly search for this channel to find out the videos. Let us start with the overview of week 12. So in week 12, so mainly three things were discussed. First one was continuation of the load frequency control. Where we were discussing the area control errors. And then next thing was the deregulation of power system. And last one was the unit commitment. So these three things were discussed. Well, the questions in this week are mostly related to this part only. For part, even in assignment you will find there are no questions related to these two topics, but you can go through the videos and you can prepare yourself for any type of questions in the exam. We'll be having one more live session, that is it will be on 16th. The timing is 6 to 8 p.m. It will be the extra live session. So there you can ask your doubts, and we will take some questions from each week, which cover the entire week. And then last thing which we will do is I'll cover unit commitment also in that. And today I will only give a small introduction to unit commitment, but in detail we'll try to do it, if time permits, in that extra live session. So you can attend it on Tuesday from 6 to 8 p.m. So let us start with the continuation of week 11. So in week 11 we were discussing that we were doing the load frequency control, and we saw that the loads are also sensitive to the frequency, which are given by this load sensitivity factor, which is D, and we have one speed regulation factor for generators, governors, which results in a which the governance have this troop characteristic. As a result of which it is beneficial to have several number of parallel generators connected in the system. So if we have more number of generators connected in parallel, we will be able to reduce and respond to the frequency in a positive manner, and also increasing the number of generators in parallel also reduces the change in frequency. Deviation in frequency is less and number of generators are connected in parallel. Okay, so we, I think all of you remember. So this is the troop characteristic. Let's say this is for one generator and this is for another generator. That can be like this. So both of them having their own slopes, different slopes. So this is frequency here and this is in megawatts. So this is slope will be high in hertz per megawatt, while D unit of D is in megawatt per hertz. The change in load per unit change in the frequency. So it is sensitivity of the load with respect to the frequency. You can also write it both of them in per unit. So it will be per unit megawatt per hertz, and this will be hertz per unit megawatt. So suppose initially frequency was at this level, right? Now suppose, so generation was here, which let's say PG1. Now let's say if the load has increased, so what will happen? So this was F0. Because of increasing load, the frequency will reduce, right? Frequency will reduce. Let's say this is the new frequency due to increasing load. Now frequency is reducing because load is increasing. So what should we do to again bring it back to the normal frequency? We need to close that difference between load and generation. So we need to, since load is increasing, so we need to increase generation, and from this troop characteristics we can easily say that if at that frequency F0 this one was PG2 and PG1 not, then these two are the new generation. That means the increase in load is being supplied by the increase in generator. So this troop characteristic automatically takes care of that. This is 2. So whenever there is increase in frequency, it will reduce generation. When frequency decreases, it increases the generation because of the negative slope. That is why we have this troop characteristics always have a negative slope. Okay, let me add one page here. Insert. Yes. So I was saying the troop characteristic is always like this. These are negative slope. These are different troop characteristics. So this will, let's say this is R1, this is R2. So can you tell what will be the relationship between R1, R2, R3 and R4? So these are slope. Hertz per megawatt. So you can easily say from slope R4 is more than R1 because for a 1 unit megawatt change in generation, increase in generation, one megawatt change in generation results in a highest, you can say most change here for R4. So this is, you can say F4. Here change in frequency is F3, which is lesser. For F2 it is even lesser, and for F1 it is least. So that means R1 is least. The change in frequency is very less here for this governor. For R4 there is a steep change. Because slope is steeper. So this is negative slope. That means if frequency increases, so generation will reduce, and vice versa. If frequency reduces, generation will increase. And we want that. If frequency is increasing, we want generation to reduce. And if frequency is reducing, we want the generator to increase, generation to increase. That is why we have a negative slope here. If we have positive slope, this is for negative slope, which is as the actual tooth characteristics. And this is frequency will increase. If frequency increases, generation will also increase, and if it reduces, generation will also reduce. So this will happen for a positive slope. That is why we don't use it, because we don't want the frequency to go haywire when the generation is increasing. We want to control it. So we want an inverse relation between the frequency and the generation. That is why we have a negative slope. Not the positive. Okay, so we have, this is very important. Okay, that was the thing I was talking about. Then we saw that so here, suppose there is overall change delta PL, change of load. So this is for a multi-unit isolated system. For a single unit isolated system, let's say here write for system in steady state, delta Pg is equals to delta PL. But in multi-unit isolated system, there are more generators. So delta Pg total will be equals to delta PL, but individually this total change in generation will be divided among the total number of generators. Let's say there are n generation. So 1, 2, 3. And how much percent of this will be shared by each of them is given by a term called participation factor. And that can be seen here. So A1 here is participation factor for unit 1 up to, similarly A2 for unit 2, then AN up for the nth generation. So this is change in frequency, and we are using an integral control here because we want final steady state error to be 0. So this is integral control, and we want that change in frequency to be compensated by or balanced by all the generators. So this signal U is shared among all the n generators, and individually they will generate a control signal U, U1, U2 up to UNN. And so this A1, A2, AN is given by a participation factor. Then so first of all we discussed a single unit isolated system, then we discussed the multi-unit isolated system. Then finally we discussed two control. Two control area. In a power system, we have two areas, and each having multi-unit or single unit. In practice, there will be there are areas, and in each area there are several units. Let's say if we compare India with the areas, then in India we will find there are 5 areas, control areas, and each of them having several generators. So 5 control areas. One is northern grid. Let's say northern grid. Then it is eastern and southern zone. Then we have central. That's right. So first is north zone, then south, then eastern, northeastern, and western. Okay. So we have these. And in each of these, they consist of several states, and each state is having its own generation states. So there are so many generators in one area. In practice also you can see this. So we will see again here when we see deregulation. So we came to the concept of control area. So load frequency control of a 2 area interconnected power system. So we have area 1, area 2, where bus 1 voltage is V1 angle delta 1, V2 angle delta 2 for bus 2, and in between there is a transmission line, 3-phase transmission line, over which transmission of power can happen in either of the direction from area 1 to 2 or 2 to 1. And both the buses also have loads. So by simple equations we can write current I12 is, we know this, V1 minus V2 divided by JX12. X is the impedance and we neglect the resistance here. So we can write power P plus JQ is VI star, and so P minus JQ we can write as V star I. So if we simplify it, so we will get this. If we assume that the initial power flow was this base power flow, initial power flow. So this much is the power flow over the tie line V1 V2 sin delta 1 minus delta 2 divided by x12. Now if there is a small change, we want to see how things happen. So we are trying to linearize the system. If you have any non-linear system, you can do this by using perturbation. So just give a small perturbation in delta 1 delta 2, you will see a small change in p tie. So that we can represent. So here we can see easily, we write p tie as this, and we replace this p tie 1 to delta 1 delta 2 by their base value and an incremental change. So delta 0 plus delta 1, delta 2 0 plus delta 2, then p tie 1 2 0 plus delta p tie 1 2. So if we simplify it by making these assumptions that since the perturbation is very small around the steady state, this initial the initially we can say this is one of the stationary points, initially steady state, then that perturbation is very small around that. So we can make this assumption that cos of a very small angle is 1 and sine of that angle is delta, same angle. So here we are making that assumption. If we simplify, then we will get this delta p tie 1 2 is this, cos into delta 1 minus delta 2, and this we can say this we write as t12, and so 2 pi t12, and this we can write it as, because delta we know that it is omega is d delta by dt, and we can write omega as 2 pi f. So this will be 2 pi f into d delta by dt. So delta we can write it as integral of 2 pi f1 t delta f1t. Same thing is written here. And if we take ratio of these two, we will get this. It is proportional to this. This is known as area capacity ratio. So finally we are interested in finding out the steady state deviation in power flow, as in tie line power flow as well as in the frequency. So this is the equation for area 1. So this is delta Pg1, or we can write it as delta P mac 1, so minus delta PL Vm minus PL minus delta P tie 0 1 2, which is equals to this kinetic energy term plus the change in load because of the frequency. So this is because of the load frequency sensitivity. So in steady state, because we are interested here in steady state, so this dynamic term will go to 0, derivatives, all derivative goes to 0 in steady state. This we make to 0, and delta f1 we can write as delta P1 minus delta PL divided into Kp1 by 1 plus STS. This is because of the integral control. Okay, so we get this as delta f1. Similarly, we can write same thing for delta f2 also, and if we have these two equations, which is here control input u1 u2 are 0, and delta f1 and delta f2 will become equal in the steady state. So we have these two equations, and we have two more equations, that delta Pg1 is equals to minus delta f by r, which we have seen from a isolated system, single unit isolated power system. So this is from that. So finally we get these two expressions, and these two expressions are very important for us. If we write A12 as minus 1, that means that rated power in both the areas is same. Then it will become minus 1. So this become delta steady state is minus delta PL1 plus PL2 divided by D1 plus D2 plus 1 by R1 plus 1 by R2. And we can also write it as, if we can write it as, so if single unit we remember we have seen this formula, no? This is for single units. Delta F is minus delta PL upon D by 1 plus R. For multi-unit we have also seen this is minus delta PL divided by D plus sigma 1 by R. Well, this is R equivalent. You can replace it by R equivalent also. So this is a generalization from that only, and we can easily see by putting A12 as minus 1 we get the same results. Here also you will get delta P tie is equal to D1. If you put A1 as minus 1, the denominator is same, D1 plus D2 plus 1 by R1 plus 1 by R2. And this is the same, another one special case where we consider the delta, the change in load is there is in only delta in area 1, and D also considered 0, R also same, and A12 is minus 1. Then we get this delta F is minus delta PL divided by 1 by R1 plus 1 by R2, and P tie becomes minus delta PL by 2. So from here we go to the area control array. So either you remember these two formulas or you simply remember these 4 equations and you just solve them. You will find the answers. No need to remember formulas, but these equations are simply very easy equations. You can directly remember them. So either way you can think. I find this is a better option. Very easy to remember, no need to remember anything. The formula is if one sign of, if you make a different sign here or something you change, then answers will change drastically. So it's better to use same base. So now area control error. So area control error depends upon these two things, and it is actually governed by the imbalance in load and generation that affects this. So it is depending upon two things. One is delta F, change in frequency, and second is change in tie length power flow, delta P tie 1 2. And so this is delta F1 A2 A12 into delta P12 is for area 2. So so delta F comes out to be minus delta PL upon D plus 1 by R equal. So B1 is D1 plus 1 by R1, B2 is D2 plus 1 by R2. So this was the main thing, area control error. So you can remember these things. You will also solve questions, and there it will be more clear. Now we will go to the second part of the week 12, which was the deregulation. Let me read one page here. One side, one page. So we have vertically integrated system. So before deregulation we can easily see deregulation, that means, or it is also called re-regulation. Either regulations which were governing the power industry, power sector, they were changed, re-regulation, new regulations came into being. Or deregulation means something which was going on before is now revised. It is changed. It is D means removed. It has been changed. So what we can see, yes, there are two things. So before, let's say before, in India it was before the Electricity Act of 2003. Indian Electricity Act. So before this, we were having VIUs, or we call them vertically integrated utilities or entities. So we are having these vertically integrated entities, and what they were doing, so there was a vertical integration between transmission. So we have a transmission, then before transmission we have generation. Generated power needs to be transmitted, so before that we need generation. Then we have transmission through our long distance or these high voltage transmission lines, HVACs, EHVACs and HVDCs. Then we have distribution system, which caters to the loads at lower voltage levels. So one of the loads we ourselves are one of the loads. Our homes, we receive power supply through this distribution system, which is connected to generation via transmission. So vertical integrated utility means that all these three functions are carried out. So all these three functions are carried out by the same entity, or they have only a single owner. They are owned and operated by one single entity. So generation, the same company will be having its own generation also, transmission also, as well as distribution. Everything same company. So that means, so there could be multiple vertical integrated utilities. Let's say we call them VIUs. So what I can say, VIU1, VIU2, VIU3. So they could be connected via these tie lines. Multiple such integrated utilities, they are connected by T line 1, 2, 1, 3 and 2, 3. So these are the transmission connecting these three vertically integrated units. But let's say there is a load here in area, let's say this is area 1, this is area 2 and this is area 3. If we have a load here, and because it is connected to VIU2, let's say it's a distribution load, it's a customer at single phase. And it is connected to VIU2 through at loads at distribution level. Now this is connected at distribution level to VIU2, and because in vertical integration the generation, transmission and distribution is owned by the same company, and the load is connected to the distribution company, to the distribution network of the second entity, so it will have no choice but to use the same generation. So that load will be fed by the same generation owned by that company itself. It cannot, it has no provision to take power from generators in area 1 or 3. Let's say the generation here is at a rate of 4 rupees per kilowatt hour. Here it is rupees 3 per kilowatt hour. It is 3.9, and let's say here it is rupees 5. Now we see the generation here is cheapest, but the load in area 2 is forced to take this generation, which is a costlier one, because there is no provision for interoperability, transfer, interchange or exchange this, so it will have to do this. But suppose if the owner, if the generation or storage or the energy or load has the facility to do that, still power with each other, then how things will change. So how that things will change dramatically. So that was the idea to move from this to deregulation or re-regulation. One of the ideas, not the. So it helps, it provides consumers with more choices, more informed choices. With smart grid we can further increase that we can provide those choices in a more smarter way. But this is the facility which the load has here to increase in the number of choices, and the consumer can choose the best which it thinks is suitable or the best for him from the economical point of view. So in deregulation, these three entities are not owned by Simple. So here we can see without IPP, if you consider there are no IPPs, IPP can also be incorporated in VIUs, but generally if we take initially there were no IPPs, so they were simply a single entity which is covering this. So here also you can see VIU is this only. This box, black box is the VIU. IPP is not a VIU. It may take power from somewhere, but ultimately this consumer will have to only take power from this VIU only. This is what the utility itself. This utility may be purchasing power from this IPP, but consumer are bound to use this power only. But now the things can change. In deregulation, this generation is a different company, transmission is a different company, and distribution is also a different company. All of the three have become three different companies instead of a single one which was there in the vertically integrated utility. So now three companies for each of the function. So now there can be multiple GenCos, generating companies. So NTPC is one of the example. Then we have NPCIL, that is for Nuclear Power Corporation India Limited. Then we have NHPC, National Hydropower So many companies are there now. And we also had these distribution. We don't have for distribution company. We have data. So now distribution companies also there are several. Oh, sorry, this is for vertically, but in deregulation these three will be three different companies. So we have Disco, Transco and Genco. Let me add one more page here. So now we have Genco, different company. We have Transco, a different company, and we have Disco, a different company. All these three. So Genco, Transco, and Disco, these companies, and they also have. So they can have several generation companies. So the transmission, each state will generally have its transmission company. And distribution companies. So in Maharashtra, you can say it is biggest distribution company is So it is in Maharashtra. It is. They also have Adani. Then there is also Adani. We have Tata Power also, and there are some other small distribution companies also, utilities. So now Discom is a different company, Transco is a different company, and Genco is a different company. Now both Genco and Disco, they need to pay the Transco for the usage of their network. So the transmission company or the Transco is building the network, and it is allowing the generation and distribution companies to transfer power over that asset which the Transco company has, transmission company has, and in return the Genco and distribution companies they need to pay the tariff for that, for the usage of network. So it is you can say it is transmission usage cost allocation framework. So all these things are done, and then now earlier what is happening that a particular load in particular integrated utility, it is bound to take power from generation in that particular integrated area only. But now here we have several consumers, I can say even several discos we have, and those discos, they are free. Even some big generators company, they are free to contract with any generators. So now Disco and Genco can enter into a bilateral contract. And all these information of these bilateral contracts they are all verified or they are accounted, because we need to know how many contracts are there so that this network is used properly, Everything is governed by a particular body which is called as the ISO system. It is an independent system operator. So Transco it builds and owns the transmission assets and its maintenance, everything. Then this entire framework is governed by ISO, which is monitoring everything. So all these transactions are carefully observed by ISO. So in India, and let's say for if you take India, we can have, there are several, each state has its own distribution company. Generally it's a public sector undertaking or state undertaking, then state PSUs, and then there are some private also discos available right now. Just as I gave you example in the previous slide that in Maharashtra we have MSCDCL, which is Maharashtra State Electricity Distribution Company Limited. Then we have private entities like Adani and Tata Power, Adani Energy Private Limited, something that's like that, AEPL Private Limited. Then we have also Tata Power. Okay, so these are distribution companies. This is for one state, let's say Maharashtra. In other states also there can be several discoms. In Rajasthan, so there are several distribution companies, even government also. So there is JVVNL, Jaipur Vidyut Vikas Nigam Limited. Then we have AVVNL, Ajmer Vidyut Vikas Nigam Limited. And similarly Jodhpur, JD, I don't remember exactly. So similarly we have several discoms, even government also several discoms for different districts, or one state is divided into several regions and they have their own distribution companies run by state government. And there can be some private also within each of these areas. Then Genco, we can say government companies. There are private Gencos also. They are called IPPs, independent power producers. Then they are government companies also like NTPC, NHPC, hydropower, thermal power. Then NPCIL, nuclear power corporation. So all these are there. And they can enter into bilateral contract. Generally bilateral contract can be over different time horizons. It can be short term, it can be long term, and medium term also, in between medium term also possible, and long terms. So in India and the remaining, we also have a market also, where these generators can bid and discoms can bid and generation can provide their offers. And there is bid matching, and overall settlement process is there. So which generator will get how much and at what price, which consumer will get how much, and how much that consumer need to pay or discom need to pay. So generator may provide such kinds of bids that he is ready to provide this much amount, let's say 100 megawatt at 2 rupees, Another generator will provide another 100 milliwatt but at a higher price. So we stack all these bids for generator, and consumer naturally, if it wants to clear in the market, the discom need to bid a higher price. So consumer can bid high and we stack them in decreasing order, and the point where this intersection decides the market clearing volume. So this much volume will be cleared in the market, and all the generator will get this much money, market clearing price, and each discom will have to pay this much, and these are not cleared in the market, the generator. So this is the actual, so this is price here and this is the volume. So this is the social welfare, and all these things, this is market monitoring, and everything is market monitoring. All this monitoring is done by the independent system operator. This bid matching and all these things, they are provided by the market. Different market platforms are there. In India we have 3 markets operational. One is IEX, Indian Energy Exchange Limited, one is PXIL, Power Exchange of India Limited, and one is Hindustan Power Exchange, HPX, Power Exchange Limited. So they do this kind of activity. They will provide a platform where generation and discoms, Genco and Disco, can come and offer their provide their offers and bid, which are matched together by these markets. So different markets have different these generators and discoms. They need to register on that platform on these markets, where they will be this mechanism will be discovered. Once this everything is cleared, the MCV and MCV, how much each generator will pay, how much bid is cleared for each generator and discom, that will be shared to the network operator, the ISO, and then ISO will have to verify it, whether that much transaction is possible or not. So this is market. It can happen at a real time market. For this is for every 15-minute time block. Then we have day ahead market, which happens one day before for each of the 96 time blocks. So we have 24 hours, and each of these hours are divided into time blocks 1 to 96. One time block is for 15 minutes. Each of them is for 15 minutes each. So in day ahead market, the bid and offering is done for this bid matching is done for each and every time block for the next day, and in real time it is done for the next time block. So real time market will happen on the D day, and the DAM will happen. Day ahead market is for the it will happen for the D day before one day. So it's on a day ahead basis. So for tomorrow, all the 96 time blocks, which generator will generate how much, which consumer will consume how much, all this will be cleared in today itself. And all these things is verified by ISO. So once the ISO will verify that yes, this much volume network can support this much volume, they will give a clearance. If not, then they will ask them to reduce the market volume, clearing volume, and that will also, and some generator or consumer might that will result in load curtailment. That is certain. So for day ahead market, if this happens, then those discoms, they still have an opportunity to participate in the real time market, where they can again quote a higher price, and if they want the demand to be satisfied, then they will quote a higher price, and they are more likely to get their bid cleared in the real-time market if they quote a higher price. So nowadays in India, Indian markets, we have a cap of rupees 10 per kilowatt hour. So this is the price, market clearing price cannot go beyond this in day ahead and real time market. And there is then beyond this also there is a high price market where also there will be the price will be more than 10. High price day ahead market, high price real time market. So in both day ahead market and real time market, this is the cap on the market clearing price. So we discussed Genco, Transco, Disco, and they are monitored by the independent system operator. Then everything, these transactions happen over a market also. This is open access. So there are other types of market. This is day ahead. We have term ahead market. We have green day ahead market. This is green is GDAM or green day ahead market. Only green energy is sold here. So the renewables, they can participate in DAM market, green day ahead market. Suppose, so if a renewable generator, solar plant is there, and because all these generators, they have to forecast their generation one day before, so that for next day they need to tell ISO. Means ISO not directly but through ISO. Also in India we have a structure for ISO. At the top we have for entire country one National Load Dispatch Center, and this is actually POSOCO, Power System Operation and Control, Power System Operation Corporation of India Limited Corporation. So this is also National Load Dispatch Center. So this is the ISO for India, Independent System Operator. Then I told you that we have 5 regions, 5 areas, control areas. So each of them have a regional load dispatch center. And in each of these areas, because there are several states, we have state load dispatch center. So these generators will communicate to the SLDCs one day before that for each time block we are going to generate this much. And they are permitted a deviation of around plus minus 15%. Let's say we will say plus minus, okay. Plus minus 15% is possible. Suppose if a solar plant has already given its forecasted schedule for the next day for each of the 96 time blocks, and let's say for some of the time blocks it goes beyond this, it generates more than this deviation also. Then what it can do, it is foreseeing, let's say in 4 p.m. it is able to generate more than this, and it can see that the similar weather condition still prevails for next 1 hour. Then next 4 time blocks in next 1 hour, the generation can sell in the real-time market. It is possible. And it can also see that today it had happened, and that tomorrow weather forecast is also good, and same solar radiance could be very high, so it can sell it in day ahead market for the next day. So all these things are clear, I think. In detail I have explained. So many things can be done. And then we also have unit commitment, third part. So unit commitment maybe we can see in the extra class. Let us go with the questions. If time is remaining, we will take the I will explain the unit commitment part also. So we want to see the questions now. So this is the first question. So we'll use the simple equation that we have already said. Without remembering the formula also we can directly get the answers. So this is the first question. Question is, consider a 50 Hz 2 area power system connected by a tie line. 100 megawatt of load has increased in area 2. So delta PL2 100 megawatt. I need to check something. I think there is some. Okay, let us see. There is some error here. So load has increased, that means delta PL is here. How much? It is 100 megawatts. Let us write it in per unit. So it will, in per unit it will be 100 divided by 250. So it will be point, how much? 0.4 per unit. Yes, 0.4 per unit. Okay. So this is happening in area 2. Delta PL2 and delta PL1 is no change in here. Now we know, we have to remember these two equations. Delta Pmax1 minus, we saw delta PL1 minus delta P tie 1 2 is equals to, one was dynamic part which is kinetic energy part, another was a constant part, steady state. So it will be d1 into delta F1. Right, d1 into delta F steady state, delta F1, and we know that delta F1 is equals to minus delta F. You can write steady state here, or it is same. So delta F1 is equals to delta F2, and this is minus delta F by R2. Sorry, delta Pmax 1 is minus delta, and delta Pmax 2 is minus delta F by R2. Delta F1 is delta F2 in steady state. and this is Pmax 2 delta PL2 minus delta P tie 1 2, and this is D2 into delta F, and delta Pmax 2 we have to write it as this one. So here it will be plus. Here you can see it here. Yeah, this is for IS. So you can write delta PL1, let me write it here. So you can write minus delta PL1 minus delta P tie 1 2 is equals to D1 plus 1 by R1 into delta F. Similarly minus, so delta, here change is happening in area 2, no change in area 1, so this is 0 actually. PL1 is 0 here. This is minus delta PL2 plus delta P tie 1 2, it is equals to D2 plus 1 by R2 into delta F. Now we need to solve these two equations and find out delta F. From here you can substitute delta F here. So here delta F is equals to minus delta P tie 1 2 divided by D1 plus 1 by R1. So you can write it here D2 plus 1 by R2 into D1 plus 1 by R1 divided by minus delta P tie 1 2 minus delta PL2 plus delta P tie 1 2. I have made some mistake here. Oh yes, I have made. This should not be here. It is minus delta P tie 1 2 divided by D1 plus 1 by R1. Now we can multiply it here, so it will be delta P tie 1 2 D1 plus 1 by R1 plus D2 plus 1 by R2. This is equals to minus delta P tie 1 2 sorry, another way is to, an easier way is to just add these two equations to remove P tie, no? So it will be minus delta PL2 is equals to delta F into D1 plus D2 plus 1 by R1 plus 1 by R2, and delta F is equals to minus delta PL2 divided by D1 plus D2 plus 1 by R1 plus 1 by R2. Everything is given here. Minus delta PL2 is minus 0.4 divided by D1 is given 0.6 plus 1.2 plus 1 by 0.05 plus 1 by 0.08 minus 0.4 and this you can calculate delta F. How much can you calculate? How much is this? 0.6 plus 1.2 plus this is minus 0.011618. So this is delta F in per unit. So this will be how much in multiplied by 50 in hertz is 0.583. Let me check once again. Is the question correct? Just a minute. I don't know, I think there is some yeah, this is the correct question. I think there was some error which is I will correct it while posting the presentation, the solution. Actually this is the correct. So there is a load curtailment. You can make it increase also, it will be positive. So this will remain same, but it is happening in area 1. So delta F will be, instead of minus PL2 here, it will be minus PL1, and this will be same D1 plus D2 plus 1 by R1 plus 1 by R2. Everything else is same, and this is actually there is a load curtailment of 50 megawatt. So delta PL1 is equals to minus, increase is positive, so this is 50. So load curtailment happens when frequency should increase, load is reducing, so delta F should be positive. That is correct. So that way it is correct. So it will be 0.6 plus 1.2 plus 1 by 0.05 plus 1 by 0.08. Now this is the final answer. It is 0.6 plus 1.2 plus 0.05 inverse 0.6 plus 1.2 plus 0.05 inverse plus 0.08 inverse multiplied by 50. So this divided by 250 we have to do now. How much is the base NV here? Oh, sorry. In this question I will have to change. Sorry for the mistake. The method will not change, only the answers values may change, but method will remain same. Don't worry about the values. So in final PPTs I will change everything. Sorry for there is some mistake from my side. So it is 0.01. 0.1 divided by this value. So you can calculate this. So how much is this? You can calculate. This is 0.1 divided by plus 1.2 plus 0.05 inverse plus 0.08 inverse multiplied by 0.1. So it is, and if you multiply it, so this will be in per unit. You multiply it by 50, you will get in hertz. So in hertz it comes out to be point. Okay. So let me just tell you the method. You can find out the answers. This is 0.8 and this is 1.0, and finally you will get this as 0.10684 hertz multiplied by 50. So this one is in per unit. So you will get 50 plus delta F. So it will be 50.10684 hertz final answer. So it is continuation of that part only. Second question. So this is 50 megawatt of load curtailment here, and that too in area 1. So this is not there. So we want to find out what happens. Tie line power flow. What happened to the steady state tie line power flow? So we have already calculated the frequency, right? Delta F. So P tie also we can calculate from here. And we can also see that because delta F here is positive, and there was, this is area 1, this is area 2 here. So frequency is increasing here because load is reducing here. Because frequency is positive, load is reducing here, so there should be generation is excess here, so it should flow here. So P tie 1 2 has to be positive, and we can also see from here this P tie. So we see minus delta P tie is equals to D1 plus 1 by R1 into delta F. and because this is beta 1 2. Beta 1 2 is d2 plus 1 by r2. Because delta f is positive, so beta 1 2 comes out to be positive. So there will be a flow of power, Thailand power flow from their power flow will increase from 1 to 2. That means it will decrease from 2 to 1. So power flow from area 2 to 1 will be decreased. Now this is the next question. Magnitude of change in Thailand power flow we want to find out. Now it is the same question here. So this is area 1 here. So 50 megawatt of load curtailment occurred in area 1. What is the magnitude of change in Thailand power flow at steady state? Let me check the question once. Area 1. This is question is correct. So delta beta we have already seen. I wrote the formula in the previous slide also. It is d2 plus 1 by r2 into delta f, and delta f we had already calculated before. So 1 plus d2 is 1 divided by 0.04 multiplied by delta f in per unit, and delta t will be 0.0555 per unit, and multiply it by 500, you will get the final answer 0.0555. It will be 27.77 megawatt. So it is C. Answer C is correct here. Is this fine? Okay. So answer C is correct here. Similarly, the next question we need to do. Okay, what is the next question? Next question is this. Continuation of that. This is area 1. Load curtailment 50. What is the magnitude of steady state change in mechanical power output? And we already know that mechanical power output is delta P max output in area 1. So delta P max 1 is minus delta F by R1. So only those equations if you use, you can solve all the equations. You are able to solve all the equations here. Because what was happening in area 1, the load has reduced. So what should happen? Since load has reduced, the generation should also reduce, right? The frequency has increased, so we want to reduce it again. So here we can see delta P, it is always a negative sign here. If F is increased, because we saw the droop characteristics. So delta F is positive, so delta P max has to be negative. So it is minus 0.002137 divided by R in area 1 is 0.0. You can find out. This is 0.0427, and you multiply it by 500, you will get 21.37. So minus a reduction of 21.37 megawatt. You see, although the load curtailment was 50, the generation reduction is not 50. It is only 21.37. You know why? Because of this D, sensitivity, frequency sensitivity of load. Here you can see it is 0.8. So when the frequency is increasing, the load is also increasing. ठीक है, इसीलिए क्योंकि फ्रीक्वेंसी बढ़ रही है लोड इंक्रीज हो जाएगा. अब लोड इंक्रीज हो गया तो जनरेशन को रिड्यूस होने की ज़रूरत क्या है, कम है. I think next part is what will happen to the governor in generation in area 2. तो वो भी इजी है ना. सिम डेल्टा पी मैक 2 is equals to minus delta F by R2. So R here is 0.04. So you can calculate this. What is the answer? 0.002137 divided by 0.04. So for a load change in 50 megawatt curtailment, in both the areas the generation is reducing. But if we sum the reduction, it will not be equal to 50 megawatts. Let us do it. So earlier it was 21.37 minus megawatt. Let's just see how much is this is in per unit. So multiply it by 500. So you are getting 26.712 megawatts. So 21.37 plus. So this is 48. So load is reducing by 50 megawatts, but generation is reducing by only 48.0825 megawatt. So there is a difference of around how much? 1.9175. So this much amount the load has increased because of increase in the frequency. Okay. So this one was the question number 5th. So question number 6th we want to see. This we have done. This is already done. What is the steady state change in total load? Yes. So that is the next question. Considering frequency sensitivity of load in area 1 in megawatt due to change in frequency. So now we want to know the change in load in area 1. We know that delta P load is equals to D1 frequency, because frequency is increasing, so load is also increasing, load is changing. Load is not constant because it is sensitive to frequency. That's why it is written here, considering frequency sensitivity, sensitive loads in area 1. So D1 is 0.8 multiplied by frequency in per unit of 0.002137. So this will be delta P load in per unit multiplied by multiplied by 500. You will get 0.8548. 0.848 megawatts. We'll see. This we found, no? This 50 minus 40. So total load change here is happening 48.0 825 minus 50. So it was around 1.9175. Now we'll match these. This will match. We'll see. So this is very interesting. You need to, whenever you solve questions, you need to see such things. How these questions are related with each other. All these are part of a single question made into different questions, but actually it is a one question. This is 1 into delta F 0.002137. This is in per unit. Multiply it by 500. 137 multiplied by 500. So this is 1.0685 and add this 0.8548. So it is 1.92. Here 1.92, right? So same thing. You will get both the answer as the sum of this will be same as that. So look for the just look for the decimal places and you will get more accurate results. So these are the first 7 questions. Now last 3 questions we will do. Now this is the third question. So it is based upon, first of all, do not fear by looking this 3 area system word. You might be thinking that we have only studied about 2 areas, that considering 2 area system also becomes so complicated. If I use a 3 area system, then I will have to derive everything, how complicated it will be. So don't go by the size of the question. First of all, read it, see what the question is asking, then you will see simple concepts we need to remember, then we will be able to solve the question. So here let us first read the question very carefully. So for a 3 area system, a load of 10 megawatt is suddenly increased in area 1. So delta PL1 is given as 10 megawatts. And generator installed in these areas are 100 MVA, 200 MVA, 400 MVA. So this in per unit it will be 100 divided by 100, which is 10 divided by 100, which is 0.1 per unit. Speed regulation are 8%, 6% and 10%. So let us write all these things. R1, let me just draw a very good diagram, so it will be easy for us. It is always good to have pictorial representation. Things become very easy to visualize. So these are the tie lines connected in between these 3 areas. Tie line, that we can call them T12, tie line 2-3 and tie line 1-3 or 3-1 you can call it. And that will only change the convention. If we take 1-3, that means we consider that the power is flowing. 1-2-3 you may take otherwise also, that depends purely upon your convention, but answer will not change based upon that. So these, it is already given that these are speed regulations are respectively on their own ratings. Neglect the friction of generator, that means dynamism is neglected. Then the steady state frequency deviation you need to find out in hertz. Nominal frequency is 50 hertz. Consider the base MVA for interconnected system to be 100 MVA. So base MVA is 100 MVA, that is why we have taken it as 100 by this 10 divided by 100 base MVA. And because these R are given on their respective bases, respective area, we need to first convert them, we need to bring them on a common base. In the previous session we saw how to convert these R from one base to another base, right? So we saw R is hertz per unit megawatts, right? So here per unit is coming in the denominator, right? So if we want to convert, so R actual divided by R base is equals to R per unit, but this will be when per unit is in the numerator. So because it is in denominator, so we need to do R per unit will be R actual into it will still hold R base, sorry, this per unit is R in hertz per megawatt divided by that power base, P base. This is R per unit and this is R actual. So R actual is equals to R per unit into P base. So now we can write R actual into old base. So R actual will remain same. So it is equals to R per unit in old base and P base into in old base, old system. This is same because R per actual will not change, is equals to P base into new. Now we want to find out R base in new. So R base in new system will be R per unit in old system, P base in old system divided by P base in the new system. Have I made some mistake? I think I have. Yes, you need to multiply it, P base here, then you will get R per unit. So R actual is R per unit divided by P base, because P base, actually let me write it, this is very confusing, you always remember it, otherwise you will also be confused. Here this is R actual, hertz per megawatts. Now megawatt is coming in denominator and I want to convert this megawatt into per unit, then I need to divide this megawatt by a base. So actual R per unit will be R actual multiplied by P base because of this megawatt in denominator. So this become R per unit by P base. So R per unit by P base by P base. So this will become R0 into per unit R P base in new system and P base in old system. Now let me write it here. Let me explain it again because it's very confusing and you'll make mistakes. So let me write it again. R actual is in hertz per megawatts. To convert this into per unit, we are converting the power into, we are dividing this megawatt by base. So what we are doing, so R actual is equals to, and this will be now per unit. So what actually are we doing? So this is R actual and I need to divide it by, to convert it into per unit. Now this is in per unit. Let me write, this is per unit and R actual is hertz per megawatt. So this you can write it hours per megawatt into P base, and this is R actual. So this you can write R per unit is equals to R actual multiplied by P base. So R actual is equals to P per R per unit divided by P base. Okay, R actual remains same. Now this in old or in new remains same. Actual value will not change, only base value and the per unit value will change. We want R per unit in the new system, which is 1. So this is R per unit in old system multiplied by P base in new system divided by P base in the old system. We have R as 3 values, R1, R2 for 3 areas. R1 here 8%, so 0.08, 6%, 0.06 and 10%, 0.1. So this is an old base. New, let me write old system. Old base also you can write old system. This is a new base, new system. New base here is 100 MVA, and old base was their respective bases, which was 100, 200 and 400. So for this 100 MVA was the base, for this 200 MVA was the base, and for this 400 MVA is the base. So now use this formula and calculate. So for this is 0.08 into new is 100, old is 100, so this is same. This is 0.06 multiplied with new is 100 and old is 200, so this becomes 0.03. This is 0.1 into old is new is 100 and old is 400. This is 0.025. Okay, so now this was the main task here in this question. Now rest is quite simple. So here we already see it is given, first of all there is no control, second neglect losses, dependence of load and frequency is also gone. So we saw that formula was delta frequency was delta PL divided by D1 plus D2 plus D3 plus 1 by beta 1 plus, means 1 by R1 plus 1 by R2, but D, there is no dependence frequency, D is gone. So we can write it is similar to multi-area system with no D. So beta, equivalent beta we can find out. It will be 1 by R1 plus 1 by R2 plus 1 by R3. Because D1 and D2, D1, D2, D3 all are 0. You can see here, I think I have mentioned it somewhere. That was a special case or so. Yes, this was the special case. So this is a 2-area system, but here we consider that D1 and D2 are 0, and there is load change in only area 1, so delta PL2 is also 0. Delta F is minus delta PL by 1 by R1 plus 1 by R2. So this is how much? 1 by 0.08 plus 1 by 0.03 plus 1 by 0.025. You can calculate it. 0.08 inverse plus 0.03 inverse plus 0.025 inverse. This is 85.83. delta F is minus delta PL minus 0.1 divided by 85.833. So this is minus 0.001165 per unit. You multiply it by 50, you will get minus 0.058. What was happening? So load suddenly increase, so frequency will fall. So here we can see delta F is negative, so frequency will fall. Consider the ways, but find the steady state frequency deviation. So deviation is minus 0.058. Minus, so answer C is correct here. Now the next question. This is also based upon two area problem. Okay, we have 10 minutes. So as shown in figure, a 50 Hz system is a two area. Area 1 has 500 megawatt of total generation and frequency characteristics beta 1 is given. Area 2 has 400, beta 2 is given. Each area is only generating half of its generation at delta beta 1, beta 2 and retain load in area 2 is suddenly decreases by 100 megawatt. So delta PL2 is equals to minus 100 megawatt. Determine the steady state frequency in hertz without loss. No dependence on load. Here also there is no dependence on load. Delta PL2 is minus 100. Everything is given in their actual values, so we can directly use actual values only. So delta F here is equals to, we have already seen the formula, minus delta PL2 divided by beta 1 plus beta 2. Because we know that beta frequency bias setting we call it. This is frequency bias setting beta is equals to D plus 1 by R. But D we are asked, the question is saying D neglect this dependence of load and frequency. So D here is 0. So beta is 1 by R1. So beta is, that's why only beta is given here. Speed regulation is inverse of speed regulation. This is minus 100 divided by beta 1 is 150 plus. So if you see the question, the answer is very small. Very short and sweet. Multiplied by minus 100. So it is minus 0.285. So minus delta P is negative, no? So what was happening? Area is decreasing, load is decreasing, so frequency will increase. So delta F is, that's why positive 0.2857 hertz. So actual frequency, steady state frequency will be F0 plus delta F, which is 50.2857 hertz. 50.2857. So answer A will be correct. Now this answer is correct. This is done. Now move to the next question. So here what we have to find, it is the same question, but here it is saying the load is assuming that there is same thing, but you have to find steady state magnitude of tie line error. So here, you know, control is activated. You can see what was there. So no control is activated here, and because we have tie line, so with frequency load control, without load frequency. So this is assuming that the frequency control is enabled now. So without frequency control enable, we were having a frequency increase, but now the frequency control is enabled. So when the frequency control is enabled, because there is a supplementary control, and which will make it's an integral control, and we know that for integral control the steady state error is 0, and that is why there is no delta p tie. Delta p tie will be 0. Okay, delta p tie is 0 here. So see, the question was very big but answer is very small. So always read these things very carefully, whether the control is enabled or not. So here, what is the answer here? It's none of the above. But if you don't read this, then what you will do? You will start finding out these values, and we know that delta p tie 1 2 is equals to, for a load change in area, it will be equals to beta 1 into delta f. Means you can write it here. You are writing delta p max 1 minus delta 1. So delta PL1 is 0 minus delta p tie 1 2 is equals to d1. d1 is 0. This is 0. And this delta p max is known as, this is delta f by r1, and this is delta p tie. If you use this, then you will calculate using this, and you will get a wrong output. So this will be delta f. First you will calculate delta f. How much was delta f? We calculate 0.2857. And here you are saying R1 is how much? R1 is, so this is 1 by R1 is beta. 1 by R1, so beta 1 is 1 by R1. So this is delta p is minus beta 1 into delta f, minus beta 1 is 150 into delta f is 0.2857. This is minus 42. So you will get something like this, which is not correct. So always read it carefully. So here there is, this will be without frequency control enabling. But now because the frequency control is enabled, there will be no tie line power flow. In steady state tie line power flow, there will be no steady state error in the tie line power flow. So delta p tie was 0 here, and now also it will be 0. Okay. So these were the questions for today. 10 questions. Now let us see, we still have 2 minutes remaining. So I will just explain you the unit commitment part which was left. So we didn't do that. So actually unit commitment, before unit commitment we will see ED, economic dispatch. I think last time also I had talked about this. So you can say that unit commitment is economic dispatch is a subset of unit commitment problem. So difference here is economic dispatch assumes that all the generators, whatever generators are there, are on. But unit commitment, first of all, so there are 2 steps here. So one is, first of all, it will find out which means which, let me say, on and off status, right? It will find out the on and off status of each generator for the considered time period for each generator. Let's say we are only so it is, let's say it's a 24-hour problem. So for next one day we want to tell, so economic dispatch will tell you two things, that for the next 24 hours, for each hour it will tell, let's say we have 10 generators, total 10 generators, and the objective of these two are optimization problem, and general optimization problem is of this sort, this form. So this is the objective function. We want to minimize what do we want to minimize here? Here we want to, this fx here is cost. We want to minimize the cost of generation subject to some equality constraint, which is generation load balance, and there subject some inequality constraint, which are the generation technical constraints, such as each of the generation has to lie between its minimum Pgen minimum and maximum. Each of the generator has its minimum and maximum generation capability, which comes out from the capability curve of the generator. So generator cannot produce, will not generate, means it will not be, if it is on, then it has to generate this minimum amount, and if it is and maximum, it can go up to this. So if we solve this problem for a particular time, so let's say we have 3 generators, and for next time block I want to know that all the 3 out of the 3 generators I want to cater to 100 megawatts. Which generator will generate how much to satisfy this? What will be PG1? What will be PG2? What will be PG3? So this I want to know with minimum cost. So what combination of these PG1, PG2, PG3 will give me minimum cost? That will be called an economic dispatch problem. So for each time instant we do that. But unit commitment problem is it's a time coupled problem. For next one day, next day, for each hour I want to know out of the, let's say we have only 4 hours, I want to do unit commitment for 4 hours. Then I want to know out of this 10 generator how many generators should be on at each hour. And so this is first part, their on and off status. Let us say we have 3 generators only out of 10, to make it simple. We have 3 generators and the output comes out to be 1, 0, 1 means on, 1, 0, 0, 1, 1, 0 and 1, 1, 1. So here what is happening, maybe demand is also changing. Let's say demand here was 100, here it was only, let's say 90 megawatts. Here it increased to 120, and then here it was more than, let's say 200 megawatts. So now here first step, unit commitment will tell that which generator will be on at which time instant, and when those generators are on, how much that generator will produce. That is told by economic dispatch. So in that way economic dispatch is a subset of unit commitment, but actually these 2 steps, the output comes in one go itself. Although there are 2, but for understanding we can say, but the output will be simultaneously. We know the on and off status of generator, and also how much the generators which are on should produce. So here we assume in economic dispatch all the generators are on. So in one sense, unit commitment first it tells which generators are on, and then it do the economic dispatch for those generators. Okay. So everything, all these things are done so that the overall entire cost of generation for these 4 hours is minimal. In economic dispatch, these are the only constraints. There can be some network constraints also, but in unit commitment we have more constraints. We have ramp constraints. That from thermal generators they have ramp constraint. They cannot increase their generator beyond a particular limit. So within next 15 minutes, how much additional generation they can generate? There is a limit to it. And how much they can reduce their generation? There is a limit on reduction also, and as well as on increment. So both they are called ramp up and ramp down limit. Similarly, there are startup and shutdown cost associated. Whenever a generator is to be started, there is a cost associated with it. Whenever it is to be shut down, there is a cost. Then there is minimum up and minimum downtime constraint. So if a generator is on, then it has to remain on for certain time. If it is off, then it has to remain off for certain time. So these are minimum up and down constraints. There are also crew constraints. So all these constraints, if we add, then it can become a complicated unit commitment, practical unit commitment problem. So this unit commitment will further discuss on the Tuesday class. So hope to see you on in the Tuesday class. Thank you for attending the session.